October 24, 9 o'clock. So this inverter is working. I didn't have to replace the MOSFET and things. So let's see. Push the button. Okay, so the light's working. No error, 0 whatever, 02. So just to explain. The 0.1 ohm 5 watt arrived a few days ago. Yesterday. Anyway, I got it last night. And the size is 5 watt. This size, which I took out, I think it's a 2 watt. Anyway, I overrated to 5 watt so that it wouldn't overheat and become open circuit. I actually don't understand why a 0.1 become open circuit. I mean, that's the only way I can think of is that it's a manufacturing defect. Anyway, I spent several hours understanding this circuit board. It's actually one of those easy peasy design circuits. When the person is designing it, they took shortcuts. In fact, this circuit board is noisy. When I throw the scope at it, it's so noisy. There's so many spikes. And so this thing doesn't meet UL, CE, or any type of standards due to noise emission. Since it's an inverter and it would just be used as a standby, in theory, just theory, it shouldn't affect any electronic device. Now, we're in this age of technology where noise suppression or noise immunity in cell phones, and who uses radios nowadays? Anyway, radios would be impacted by this unit due to a lot of emission coming out of it. So, let me see, just to summarize what failed. So this circuit board got rained on. I don't know how it corroded the vias. There's probably a reaction, what you call galvanic reaction. So the vias with the water corroded the copper, so it became open circuit. Now I think because of the water, it's one of those things where because of the minerals or minerals in the water, in the rain, it then created a short circuit which burnt the tract up at the bottom of the circuit board. So it created an open circuit. I think the vias being corroded and the tracks being burnt, it's one event. So it prevented the 12 volts from here coming up here. Now, while during those events of water ingress, the MOSFET also got wet, and so the source to drain, probably due to that galvanic reaction, created over 20 volts between the drain and the source. No, between the drain and the gate. So it created a problem with the MOSFET. All devices have data sheets, and one shouldn't exceed the data sheet. So gate to drain exceeded the data sheet. Now, because I was too quick in my diagnosing the circuit board, I replaced this component, basically a regulator. I think it was working. Now, during the removal of this component, due to heat, the resistor R89 got damaged, and along with this other resistor, which is the current sense from the source to the to this regulator. So it was a multiple problem. For a quick diagnosing of this circuit board, apply 12 volts here on this diode and ground. This is a 5 volt regulator, 7805 M. So M specify half an amp, I think, if I remember correctly. So ground, put ground here and put 12 volts here and power it up. If it powers up and it does what it does, then you can go back to say, there's no power here. It could be the MOSFET, it could be this becoming open circuit, it could be the gate resistance. So it's fairly easy to diagnose this. These two drives these MOSFETs. These MOSFETs drive the high current MOSFETs. So you have the buffer, you have the MOSFET driver for the high current MOSFETs. So this is configured as half bridge. Now this is the micro. I think this is the JTAG. So if I knew what micro this is, I could probably figure out or reverse engineer the firmware for this, but who cares? Now, how is the auto power comes on? Basically, if everything is fine, there's 24 volts coming up here. This line here, there should be 24 volts on this line. And when you press the button, this other line here, there would be 20. It would bring voltage to this line. It's actually not 24 volts. It's around 8 or 9 volts. So this jumper, the power, you can actually remove the jumper and do all sort of tests to this circuit board, isolating this system from the 24 volts by that jumper. Anyway, this thing has two NPN or PNP transistor. So when you press the button, it energizes this transistor. The other transistor is a signal because you don't want to put 24 volts or 8 volts into the micro. It would just blow up. So these are used as a latch and a signal. So one of them, I trace the track, goes to this component, which is used to take the power from here and pass it to the regulator. So that's how this system works. So once the micro detects a button press, it would then send a latch signal to the MOSFETs or transistor, which latch that, which maintain the power to the system. Now originally, when I was doing shit and giggles, I used 0.18 ohm. This design with 0.1, the current surge is set to 10 amps. When I use 0.18, the current surge was designed for, change the design criteria to 5 amps. Now there's some design flaw in the system because 5 amps should be enough to power this system. But anyway, the design criteria was changed from 10 to 5. When the system begins to self-diagnose the system, it powers up 1, 2, 3 relays. And the immediate surge, when it's doing self-diagnosing, it droops the 12 volts to 8. Now, when these are designed for 12 volts relay. When you go from 12 to 8, it would open. The coil is not enough to maintain magnetic to keep the contacts closed or open. So it would then open up, and when this opens up, the micro detects it and say, there's an error. That's why it was giving out error 02, because it detected a fault, and it took me a while to understand that fault. So once I have the system working, it's actually okay now it's okay now, it's working. So let me just go and set up the wiring and things. So I've connected ground into 24 volts. I measured ground in 24 volts here. So all of the cables are connected, and I'm just going to press this. Kind of hard to see with the backlight. Now there is no error 02. So error 02 has to do with power glitching. It was glitching, I noticed before, and I was glitching, and I thought, that's silly. And I had to look at the data sheet of this chip and calculate the pulse current that it's supposed to be seeing. Because when this thing is switching, there is a pulse which is detected by this regulator, and it has to be within a certain limit set by this resistor. When I changed it to 0.18, I changed the parameter for the detection of the current. That's why it was glitching. Now, when this is the correct design criteria of 0.1, it's not glitching. So it's working. So I don't need to replace MOSFETs. I don't need to replace those or those chips. And yeah, I mean, when I was checking the MOSFET, I thought there's nothing wrong with them. What's wrong with this picture? I was talking to myself, of course. So eventually I realized when I threw the scope at it, there is a design criteria that I was not meeting when I was doing the Frankenstein repair, just because I just simply want to make this work. Once you have certain things working, you can then begin to slowly diagnose the main fault. So which I did. Yeah, it was fairly, well, it was fun a minute. Anyway, I pretty much, I mean, these other resistor and whatnot are what you call supporting circuitry. It has what you call safety circuitry to protect the micros. And also, I was able to determine that this, if you know what you're doing, you can convert this to 48 volts inverter. So by adding the extra relay, these, and there is jumper settings here that you can set for 48. You can make this a 48 volts inverter. So yeah, it was fun a minute. Thanks for watching.